Hi, Don Cohen here. We're going to be working on an important piece of mathematics, iteration or feedback. And it's very exciting because I don't know everything. I'm learning all the time about this. We're going to start with young people and show that young people can work on it and do a lot of good mathematics and at the same time do a lot of arithmetic. Now, don't worry about making mistakes when you're working on it. If you start early enough, you don't have to worry about it. In college, you'll have to worry about it, but not here. We're going to use calculators to help us because we're going to be doing infinite sequences in series. The important thing is look for patterns, and sometimes if you don't write the answer as one number, it'll help find the pattern that lurks beneath and makes it possible to generalize what you're doing. And in doing math, sometimes you get a simple problem and change it a little, it makes it harder. But don't let that deter you from exploring new and unknown territories here. There's always more to do, and nothing is finished. And most important here is have fun. We'll start first by iterating 2 times x goes to x. And we'll write that here. Sometimes you don't use the times sign there because that's a variable. Okay. And what we're going to do is put a number in for x, like let's suppose we take 3. So we'll have, if we put 3 in for x, we'll have 2 times 3, and of course that's 6. And then we take that answer and we put it back in for x. So then we get 2 times what? 6, right. All right, which is otherwise known as 12. And then we take that answer. See, we're always taking the answer that we get and feeding it back in to here. If you stop the tape and try this, we'll come back and you'll see Jane working on a similar problem. Jane is working on iteration or feedback. And do you want to explain how this works? Like, what are we doing? What are we starting with here?
2x.
2 times x, okay. And what are you going to do? The calculator does what? It's going to, you did what? You put a number in, right? What number did you put in? Here.
5.
5, okay. So if you put 5 in for x, you're going to get out what?
10.
10, because 2 times 5 is 10, huh? Okay. And that's what's going to happen next? What are you going to do next? What's the machine going to do? You told the machine to do it. What did you tell the machine to do? It's going to take this number and do what with it?
It's going to... It's going to put this here.
Right. Instead of the 5, it's now going to put 10 in for x, huh? So now it's going to be 2 times what?
10.
10, which is?
20.
You want to write that down? How old are you, Jane?
6.
6, okay. And then why don't you do the next one, huh? What's going to happen next?
2 times 20 equals...
You want to keep going? What's going to happen next? Now what Jane is doing is feeding back the number back in for x here every time. Now Now, what's happening to these numbers now? Like, how do you get from here to here?
This.
Is there a pattern to these numbers? Like, could you write the next one without doing any work? Like, you know what the next one's going to be.
Mm-hmm.
What is it?
160.
Yeah. How did you get it? How did you get 160? You didn't make
80
that up.
and 80 is 160.
Yeah, you doubled it, huh? Okay. Why don't you just write that number down? 160, huh? Now, this idea of feedback or iteration is not really new, but it's new to a lot of people. New to Jane? You just learned about it? Well, you saw what Jane did with the iteration, and now I'm going to just rewrite what Jane did. Remember I said before, sometimes if you rewrite and don't write the answers, you see the pattern lurking beneath. Now, what we had was 2 times 5. I'm going to try to do this with 2 colors here. All right? Which, of course, Jane got 10. Now, if we take this number and put it in for x, what is our problem? The problem was 2 times x, right? That she's iterating, goes to x. So first she put in 5, so we get 2 times 5. Now if we take that answer, which she had as 10, and put that in for x, we get what looks like this. We get 2 times, and then we're going to put that in, so we get 2 times 5. And I'm beginning to think that doing math in color is very good. So now you can see something happening. This is the first one, this is the second one, and what do you think is going to happen next? Well, we're going to take all of that, put it in for x. This is otherwise known as 20, and you take 20 and put it in for x, and we get 2 times 2 times 2 times, let's see, do I have the right number of 2's? Yes, okay. Counting sometimes is not simple. So here's 1 2, and there's 2 2's, and then 3 2's. And if we want, we could write this with exponents, which would make it even simpler. This 2 times 2 is otherwise known as 2 squared times 5. And then this is going to be what? 2 to the 3rd power times 5. And now you can see a nice pattern going there. And if we generalize, if we keep going on and say we'll take the nth one, then this is going to be what? How are we going to generalize? That'll be 2 to the nth. What do I do? I guess I'll use n here. Times 5, huh? So, in writing the numbers out, instead of writing 10 and 20 and 40, doubling each time, as Jane said, if we write it this way, then we can use the little exponents here to generalize what's happening. Now, Jane's problem was fairly simple. What happens now is that if you change the numbers in Jane's problem, instead of, what was it, 2 times x goes to x. If you change it like to 1.1 times x, this now becomes a problem of compound interest or population increase. And the problem is, suppose a town has a population increase of 10% a year, all right? And this 1.1 would be like 100% plus 10% times whatever the population was. So suppose the population starts with 1,000. We get 1.1 times 1,000. We can use the multiplication sign here. And that's 1,100, huh? No, yeah, 1,100. So that's 100% plus 10%. 10% of 1,000 is 100. 100 plus 1,000 is 1,100. So this would be the population after the first year. Now after the second year, you would take 1.1 times what you had, put this back in for x again, and 1,100 here. And if you know 11 times 11 is 121, then this is a little over 1 times 1,000, so it's got to be, what, 1,210. That 121 has to be in there. I try to do the math in my head as much as possible. And what happens next? We take this, the population then at the end of the second year is 1,210, and then we take that and put it in for x again and keep doing that, and you have the population increase problem. All right, we're going to start with a little different problem, slightly harder, and that's 6 over x. We're going to iterate 6 over x. Suppose we put in, what, 2? All right, we'll put 2 in for x. And we'll have 6 divided by 2. And what's 6 divided by 2? That's 3. All right, now we take that answer again and we put it in for x over here. And we now have 6 divided by 3, which is otherwise known as 2. Now, if you stop the tape and try some numbers yourself, try different numbers, see what happens. You might even want to try to graph the input numbers versus the output numbers. We're going to start with 6 divided by x. All right? And we're going to put in a number, and we're going to get out a number, right? And then we'll put that number back in. All right. You want to pick a number? Small number?
2.
2. Okay. So if we start with 2, and you put 2 in for x, what are you going to get? You're going to get 6 divided by 2. Do you know what that is? Like how many 2's make 6?
3.
3. Do you want to write that? Why don't you write that, huh? Okay, and now if you put 3 back in for x, you're going to have 6 divided by 3. And what would that be?
2.
2, okay. You want to put a comma here? And then put 2, huh?
Oops.
2, okay. And then what? What are you going to get next? You're going to put 2 in for x, huh? So you'll have what? 3. What happens next?
Maybe 2, 3, 2, 3, 2, 3.
Go ahead, do a few more, right. 2, 3, 2, 3, 2, 3. All right. And we could put, if you put 3 dots over there, that means it keeps going forever like that. Very nice. So if you start with 2, it goes to 3 when you feed it back in, and then 2 alternates, huh? Okay, suppose you start with a different number instead of 2. What if you started with
4.
4? Oh, good. All right, 4. Why don't you write 4? Why don't you write 4? We're all right. We're okay.
But we're getting some noise on the cord.
Okay. Try not to play with the cord, okay, Gene? Jane? Start with 4. Okay. So 6 divided by 4. How many 4's make 6? How many 4's make 6? You made up a harder problem, didn't you?
One and a half.
Sounds good to me. You want to write 1.5?
Okay.
Good thing we got a lot of patience, huh? All right, now you're going to put 1.5 back in. What's going to happen? How many 1.5s make 6, huh? What do you think? What's your guess?
Four.
Ooh. How did you know that?
Look, 2 and 3. 2, 3, 2, 3, 2, 3. 4, 1. So it should be 4 again.
I think you're right. And if we did 4 1.5s, let's see, 4 ones is what? How much is 4 ones?
1.
4 ones.
4.
And 4 halves. If we did a half 4 times, how much would that be?
2.
And 4 and 2 is?
6.
So you're right. And what's going to be next?
1 and a half. 4, 1 and a half.
4, 1.5, 1.5, 4, 4, 1.5, 4. So it's going to alternate again. That was good. You want to try a different number? Let's see, we tried 2 so far. You tried 4. What else could we try to start with?
1.
1. All right. Go ahead. Go to it. How many, let's see, you're putting 1 in for x, right? So it's 6 divided by 1. How many 1s make 6?
Easy. 6.
Easy, yeah. Go ahead. 6, huh? What happens next?
1.
I love your commas there. And if you put 3 dots, huh? And 3 dots up there, they keep going forever, like that. Terrific. Let's see, you tried 2 and 4 and 1 so far. What could you try now? Want to try another one? 1, 2, 4.
3.
3, okay. I bet that's going to be easy, huh? Easy, right? Okay. Put your 3 dots. Huh? Anytime you want. Okay. You want to try another one? Or I wonder if we could graph this. Should we graph? We'll graph the starting number and then the numbers that come out. Now this will be the starting number here, okay? So like we'll plot, let's see, 2, and then we'll put 2 and 3 because those are the 2 numbers. So you want to put a dot here at 2? Yeah, one of those, huh?
4.
Good. At 2, 2, here, and 2, 3, huh? There, dot there, and right above it, huh? 2, 3? Yeah. because those are the two numbers. When we started with 2, we got 2 and 3 all the time, right? All right, now if we started with 4, we got what? 4 and
1
1.5. So if we put 4, we're going to go to 1.5, right? And, yeah, put a dot there. And 4, huh? 1.5 and 4. And put a dot at 4, 4. That's okay. At 4, 4, huh? Yeah. Yeah, it's a funny looking thing so far, huh? How about 1? 1, you're going to have 1, 1. No, we have 1, 1. Because we're getting 1 out, and then 6, huh? And 1, 6. That's it. Now, did we try 3? We go to 2, 3, huh? So 3 goes to 3, 2, and 3, 3, huh? Yeah, those two. Look at that funny looking graph, huh? Now, if we do 6, it would be what? Put in 6, we would get what? If we put in 6, we would get what? 1. So 6, 1, huh? And then, yeah, make it bigger. Make it bigger, bigger. Come on, come on. Don't put a hole in it. And then we also get 6, right? We get 1 and 6. That's it. Look at that funny looking graph there. What do you think? You ever see a graph like that before? No. That was terrific. Super, Jane. Well, we've just seen Jane do the iteration, and you notice that Jane didn't say 1 remained to 1. She said 1.5 when she divided 6 by 4. I have a lot of 5th graders who still say 1 remained to 1. I'm trying to get them out of that habit. If you see the videotape on cookie sharing, which people do the fractions right away, that would help. Jane had done some linear graphs before, but like me, when she got to this graph and we plotted these points, I had done it before she did it, and it really was a surprise to me, too. It looks funny. You don't know what it is right away. And I decided to connect, and I realized that when I made this graph, which is similar, you can see the curve here and the straight line here on Jane's graph, and I just made a better picture of it to show that. And you have 2 curves, y equals x and y equals 6 over x. I mean, things are very surprising in all of this iteration stuff. The other interesting thing is that the point of intersection of those 2 graphs, can you guess what that might be? It turns out that that's the square root of 6, comma, square root of 6. Those 2 numbers are at that point right there, which is something like I was not sure of and didn't know before. So there's a lot of interesting things to find out, and I still don't know everything. We're going to now look at solving a quadratic equation. X squared minus 5 times x plus 6 equals 0. Now it turns out there are 2 numbers that make this true. And there's a secret way of finding out the 2 answers if you work at it. It's not too complicated. We're going to try 4 and see what happens. Okay, we're going to put 4 in for x. So we'll have 4 squared minus 5 times 4 plus 6 equals 0. And let's see what that is. 4 squared, that's 4 times 4 is 16. And 5 times 4, 4 4s is 16, 5 4s another 4 is 20. Plus 6 equals 0. And the question is that true or false? Well, 16 minus 20, what's that? Well, 4 is 20 minus 16. So 16 minus 20 is negative 4, right? So it's negative 4 plus 6 equals 0. Is that true or false? Right, it's false. So 4 doesn't work, and what I'd like you to do is work on trying to find the two numbers that make this true. You got to put in x in the same number for x in both places here, so you can only try one number at a time. Try a small number, see if you can make it work. X squared minus 5x plus 6 equals 0. Now you know the answer to that, the two answers, right?
Yeah.
What are they?
2 and
Okay?
3.
2 and 3. Okay. So he already knew. Now you did that by guessing or what?
I figured out because 5 is 2 plus 3 and 6 is 2 times 3.
Ah, okay. All right. Now, he did a little algebra, and then we're going to show how to do the feedback and getting some numbers here that will lead to the roots of the equation. Okay, why don't you explain just briefly, Jonathan, how you get from one step to another here.
Oh, from here I start by moving 6 over here, subtracting 6 from each side.
Okay. And then what did you do? Now, how old are you, Jonathan?
7
7
and
years
3/4.
old. 7 3/4. Now, a lot of people talk about kids needing a lot of algebra to do this stuff, and I don't think you'd need a lot, right?
Yeah.
Just a little bit. Okay, then what did you do?
Well, then I bring the 5x over here.
Okay, so you added 5x to both sides.
Yeah.
And you
then,
ended up with?
I ended up with x squared equals 5x minus 6.
Okay.
Then I divide each side by x.
Okay.
Then I got x equals 5 minus 6x.
6 over x.
Yeah.
Okay. All right. Now, here's the tricky part, and the thing that's normally not done in schools, and of course, Jonathan being 7, hasn't been inflicted by factoring and quadratic formula, and we did a little iteration. Now, do you want to explain just what we're going to do here?
Yeah. Well, we're going to substitute a number for this.
For x. Okay. Suppose we put 1. Is that okay?
Yeah.
If we put 1 in for x, okay. And then what's going to happen?
Oh, then it goes to -1.
Okay, because 6 divided by 1 is 6, and 5 minus 6 is
1.
negative 1.
1.
Okay. All right. And then what do you do with that?
Oh, then you put -1 here and it comes
Okay.
out as 11.
Oh, he knows all the numbers already. Huh? Okay, so the idea is that what Jonathan's doing is he put a number in here for x, get a number out, put it back in, get a number out, put it back in. It's called feedback or iteration. Now, Jonathan has a program that he wrote, and I think I took it off the screen there.
Program, oops.
And he wrote the program from my book, right?
Yeah, oh yes,
Okay.
program.
Is it working?
Okay. Okay, let's stop.
You all right?
2. Yeah, and then
All right, so you
program 2. Then so I put in 1.
You put in 1. Go ahead.
Then-
Why don't you just do it?
Then it becomes -1.
You
Then
get negative
11.
1. And then you get 11. And then
Then you
what?
get 4.45, 45.
Okay.
It goes on forever.
And then what?
Then 3.6530612.
All right, that's enough, huh?
Yeah.
Okay. And then
And then it keeps on going down until it gets to 3.
So it's an infinite sequence,
Yeah,
and it gets closer and closer to
3.
3. And 3 happens to be one of the two answers that
Yeah.
it should be, right?
Yeah, it's always 3 unless you start with the number 2.
Always 3. No matter what number you put in here, it'll go to 3 except for 2. What
And
about
0, you says,
and 0, right? Why not 0?
because you can't divide by 0.
Okay, so when we put 0 in, we don't get, it blows up and we don't get a number.
Yeah, it says my error on the calculator.
Very good. We just saw Jonathan solve the equation and use 1 in for x here and iterate it on the calculator. And if you start with 1, you get an infinite sequence that goes to 3 as its limit. And what we're going to do here is going to start this graph. Like Jonathan said, 1 goes to 3. So if we put 1 and then 3 is the limit of the sequence over here. And this is our guess number down here. Now 2, if we put 2 in for x, 6 divided by 2 is 3. 5 minus 3 is 2. So 2 will go to 2. So 2 is a point over there. And if we try 3, what's going to happen? Well, you know that both numbers, 2 and 3, are the roots of this equation. And if we put 3 in here, 6 divided by 3 is 2. 5 minus 2 is 3. And 3 goes to 3. And we'll put that here. 3 goes to 3 directly. And 2 goes to 2 directly. Now, if we try 4, I'm going to do 4. Mode 1, program 1 is the program I wrote to do this iteration here. And I hit execute and put in, I'm going to put in 4 for the first guess number. And then I just hit execute. I get 3.5, 3.285, and so on. If I keep doing it, boom, 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 I get closer and closer to 3. So 4 is going to go to 3 also. There's an infinite sequence that goes to 3. Now, why don't you try some other numbers and see what you get? All right, we're going to stop the tape, and why don't you make this graph? All right, and we'll come back. We'll see Jenny, who's 11. You'll see her wonderful, wonderful graph. Okay.
That's my wonderful graph.
That's her graph.
A wonderful graph.
This is the guess
A
number.
wonderful graph.
The
It's not just any
wonderful
graph.
Right.
Wonderful graph.
Like when you put 2 in, you get 2.
2. That's the only one.
That's
Because
the only time you get
That's
2.
one of the answers.
And
So
you put 0 in, you get,
nothing.
it blows up.
It
right?
doesn't let you do anything.
You don't get an answer
don't get an
because
answer.
you're dividing by 0.
You can't divide by
And
0.
now, there are other numbers that where it blows up also.
Yes.
All right? And while I was doing my book, I found this out. And I had this graph in my book, and
So he wrote in that it's wrong.
now we saw that Jane's problem, which was iterating 6 over x, and what Jonathan got was 5 minus 6 over x. Now, I purposely, you see, gave this to Jane because I knew that a small change would make it more interesting and be the root of the roots of that quadratic equation, a solution of the quadratic equation. Now, another interesting thing we can do here is take this, since this is x, right, that Jonathan had, x equals 5 minus 6 over x. If we take the 5 minus 6 over x, and in place of x here, we're going to put this, since this is x, we're going to take that whole thing and put it in place of this x here. So that becomes 5 minus 6 over x. Now, this little interesting thing here, you can keep doing forever. It's called a continued fraction. If you keep going forever, it would be an infinite continued fraction. We've been getting infinite sequences with the numbers that Jonathan picked, right, and that we graphed with Jenny. We've been getting alternate sequence here, an infinite sequence of alternate numbers, 2, 3, 2, 3, and so on there. Now, you know, you can do this at many levels and try numbers in for x here. There's a lot of things to try and see what happens. The other thing which I did here was to graph, instead of x equals, I made it y equals 5 minus 6 over x, and then I put y equals all of that, and I graphed those two on in Mathematica, as a matter of fact, on the computer, and I get two graphs here. They're both hyperbolas, and they intersect, surprisingly enough, at 2, 2 and 3, 3. 2 being one of the roots of that quadratic equation, and 3 being the other root of the quadratic equation. I mean, something I had never seen before in my life. So this is, could be very interesting for you too. I think that what we've done here is a lot of interesting things. There's no end to it. The iteration or feedback is an important mathematical idea. It leads to infinite sequences and lots of surprises. And if we start with young people doing it, it gives them a way to do important mathematics and at the same time do a lot of arithmetic. It gives a productive use of calculators and computers. We've used both the calculator and the computers here. And don't worry about making mistakes, because everybody makes mistakes. As you saw, Jenny mentioned the mistake in my book, which was interesting. Look for patterns. Try not to write the answer as one number, and that will help to find the patterns that lurk beneath and to generalize. Changing a simple problem in mathematics can often make it much harder, but don't let that deter you from exploring new and unknown territories. You're going to make a lot of mistakes, but you flounder. It's like riding a bicycle when you first start. And there's always more to do. Nothing is finished. I'm always learning new things, and I hope you will too. And most important, have fun. See you. Try to solve x squared minus 5x plus 6 like 3 or 4 other ways besides the school ways of factoring and quadratic formula and Jonathan's method. See if you can do it like 3 or 4 or 5 other ways. I think that's what got me into this in the first place, is trying to solve that quadratic equation.